Okay, so where were we? We were that if you completely neglect diffusion, if the Reynolds number is formally infinity, then the induction equation is a very, very strange equation. It basically describes a vector field that evolves a fixed topology. And that's crazy. I mean, he would say that the magnetic field had the same topology it had, you know, the birth of the universe. So obviously it can't be right. So somewhere, even though the magnetic Reynolds number is huge, there must be at least some regions where diffusion is important. You can't just plain go out and neglect it everywhere. You may be able to neglect it almost everywhere, but not everywhere. So we have this paradoxical situation. So Rm, magnetic Reynolds number, is huge. You would like to just throw it away. If you throw it away, you get into these completely, you know, crazy situations that, you know, you cannot evolve magnetic fields. You can't do anything with them. Just think of the solar cycle. No, solar activity cycle. You've got this thing that every 11 years reverses the polarity of everything. You've got, you know, leader spots become follower spots, and it does it every 11 years. So you have the feeling that whatever is operating in the sun to give rise to the solar activity cycles every 11 years to get rid of all of the flux and replace it with flux going the other way. And it has to do it in 11 years. And if there were no diffusion whatsoever, you would say this thing wouldn't be able to have done it ever. Whatever topology was there when you formed the star, it has to be the same now. But that's clearly not the case. These systems seem to be able to generate flux, destroy flux, do all of these things. So somewhere, diffusion has to be important. Okay, so somewhere, just like in the DNA, there has to be this topo 1 and topo 2, these topoisomerase that comes along and lets the field lines go through each other, reconnect. All right, so this business of diffusion is crucial because it allows changes in topology. And we observe that changes of topologies occur. And so let's have a look about the action of diffusion. You know, what is the characteristic features of diffusion acting in a system where the magnetic Reynolds number is large? And again, sort of let me do it through a series of, you know, pathetically easy examples. The feature of all of these things is they're always pathetically easy when you start, and then suddenly you find yourself in a mess that you have no idea how you got there. So things always start easy, but they don't stay easy for very long. All right. Let's assume that, suppose that you have a system with no motion. Then the characteristic decay time for a system of typical scale L that is associated with collisional diffusion would be L squared over eta. In most astrophysical situations, that quantity is longer than the lifetime of the thing you're looking at, or longer than the age of the universe, depending, whichever one comes first. So the one exception are planets. Planets, the magnetic Reynolds number ain't that large. So, you know, the magnetic field of the Earth would decay in a few million years if you didn't do anything. Since we know from looking at rocks and geomagnetism and whatever, we know that the, you know, field of the Earth, a few hundreds of thousands of years, that the magnetic field of the Earth has been there for millions of years. We know that something has to regenerate this damn thing. But if you look at the decay time of a galaxy, it's longer than the age of the universe. So, you know, for something like a galaxy, it's a good argument whether or not you need to regenerate these things. But typically, these numbers are so long compared to any dynamical time scale, so you think, no, nothing can possibly occur on that time scale. That time scale is irrelevant. Okay? And why is it irrelevant? Well, because this is the time scale that you get if nothing is moving. So obviously, the interaction on diffusion and motion must speed things up. It must cause something to happen a lot more quicker than you think. I'll look at the quickness in a moment, but for now, I'll show you that what happens when you start having diffusion interact with motion is that there are these characteristic scales at which diffusion becomes important, and therefore something diffusive will happen, but the scales are very, very small. Okay? So let's look at this totally ridiculously simple example. Okay, let's take one of the simplest fluid motions that is non-trivial. Uniform translation is a fluid motion, but it is trivial. So the next best one is a stagnation point flow, and I've just taken an axisymmetric stagnation point flow. So a stagnation point flow is what you get if I get a hose and point it at the table. The water will go down like this and splatter out that way. Okay, so, and then there will be a point, which is the stagnation point at which the velocity is 0. So the velocity is all going out over here, it's all coming in over there, and there's just one little point where the velocity is 0, which is the stagnation point, and it looks like this. And all stagnation point flows are characterized by the following thing. There's one direction in which you're going in and two directions in which you're going out, or there are two in and one out. There's no other possibilities, okay, for stagnation point flows. So the one I've taken is the one where you come in along the y-axis, come in along the z-axis, and go out along the x-axis. So this one is the inverse of spraying water on this table. It's the one where I get all the water from the table and I send it squirting up, all right, in the z direction. Okay, so this is my velocity, alpha x minus alpha over 2y minus alpha over 2z. So I'm in along the z and y direction, and I'm out along the x direction. And alpha is just a parameter that measures the velocity, okay? It's a unit of velocity shear, I should say. Okay, well, what's going to happen? All right, given the geometry that I have, if I have a bundle of field lines going this way, they're going to get stretched. They're going to get pulled, they're going to get squeezed in the sort of y and z direction, and they're going to be pulled out in the x direction. And I have an equation, and I'm not afraid to use it, so I can actually work out what the steady-state solution is for this problem. Okay? So let's assume that the field is all in the x direction, so I just have a bundle of field lines that are going like that. So my field looks like that, x, y, and z. I substitute it into the induction equation. Okay? So the induction equation, it just has the stretching terms. Here they are. They're of the form of v dot grad something. So here they are, boink, boink. Okay? So I'm pulling along the x, I'm squishing along the other ones, and then I have the diffusion. Okay? Suppose that I want to find a steady-state solution for this thing. What does a steady-state solution mean? It means that it gets to a configurations where the effect of diffusion, which is want to spread things out, so diffusion, you give it a bundle of things, it wants to make them all the same everywhere. So diffusion is the thing that gets concentration and destroys them. Squeezing does the opposite things. You give it diffuse things, it wants to turn them all into a bundle. So there's going to be a scale at which, you know, the diffusion balances the advection. So the diffusion is just capable of preventing the advection from squishing this thing into a smaller scale. So we have the equation, we can work everything out. And so this is the sort of steady-state solution. And notice there is a thing that has got, you know, this funny combination, eta at the bottom. So, you know, the smaller the value of eta, the more this thing gets concentrated. And it has an exponential profile. So if I look at the total flux in the rope, since this is now, you know, an exponential, actually it's a Gaussian. So I guess a Gaussian profile. So almost all of the measure of this thing, almost all of the flux is concentrated into the part of the Gaussian where there is the peak. You know, it has this form. It's B0 pi times the square of a characteristic length, okay, an area. And if you look at this characteristic length, it's just 2 eta over alpha. Now, alpha is a velocity shear, okay? So I can turn it into velocity divided by a characteristic length. So if I do that, which is what I've done down here, I find that the characteristic scale of this flux rope is L, well, some characteristic scale of the system, whatever it is, your unit of length, which of course determines the Reynolds number and so forth and so on, times the magnetic Reynolds number to the minus 1/2. Okay? So this is the important scaling. That if you okay, let me do it this way. If you quadruple the Reynolds number, your flux rope will become half as big. Okay? So that's the scaling that counts. Is that the size of the gradients goes as the magnetic Reynolds number to the minus 1/2. So bottom line is that if your magnetic Reynolds number is huge, is into the million or zillion, the scale over which diffusion balances advections are absolutely minuscule. They occur over a tiny, tiny, tiny fraction of the volume. Okay? Nevertheless, even that tiny, tiny fraction of the volume is what you need to allow these topological changes. Because if you think about the example we had before, we had these two linked flux tubes. And the difference between linking them and unlinking them compared to the size of these links has got nothing to do with it. All I need to do is cut them in a tiny little area and unlink them. It doesn't matter if these things are the size of the universe or not. So long as you have some diffusion, even if it acts in a very small place, so long as it acts, it can change topological things on any scale you want, since topology is scale independent. So the bottom line is that this, if you want to find a scale at which diffusion and advection balance, it goes as Rm to the minus 1/2. Okay? Now, it's a lot more complicated than that, and I shall now give a word of warning. This is a disclaimer, like the stuff on the back of, cigarette packets. If you eat this, you die. If you smoke me, you explode. If you drink too much of me, you'll have a tummy ache. So this result, with its exponent of 1/2, only applies to velocities that are smooth. So that result is correct if my velocity is a differentiable function. If it has a derivative, then that is correct. If it doesn't have a derivative, because, for instance, it's a turbulent velocity, so turbulent velocity in the inertial range, we'll come to that tomorrow, but let me just tell you that if you look at the scaling, the geometrical scaling of velocity differences in the inertial range, they go like the length to the 1/3 power. That's a function that doesn't have a derivative. All right? It's not differentiable in the classical sense. It's only Holder differentiable. And so if you have one of those velocities, if your advecting velocity is not smooth, it's not a nice axisymmetric stagnation point flow, it's a mess, it's a turbulent velocity, then this exponent is different. And this exponent will be bigger. Okay? Will be bigger. And the more non-differentiable your velocity, the more this number will approach Rm to the minus 1. Okay, but we'll cover these catastrophic cases, these bizarre, cases of rough velocities, non-differentiable functions, and odd stuff tomorrow. For today, our velocities have derivatives, and this is correct. Okay? So we're dealing with analytic functions, and everything is fine. So the other effect that you can have, if you remember, I just said, if you don't move the fluid, then the time it takes for this thing to diffuse is enormous. But if you move it, then, then not only the scales get tiny, but the time scales also get shorter and shorter. So you can accelerate the decay times by having motion. So for instance, here's another very simple example. Now, again, we have a stagnation point flow. Now, this is a two-dimensional stagnation point flow. So this is just going like, which way is it going? Yes, like this. So the velocity is coming down and going out, coming up and going out. So everything is being pulled out along the x direction and squeezed in along the y directions. And I've chosen the coefficients to be the same so that this thing here, it's incompressible. Okay? So there's no axisymmetric squeezing of this thing. The volume is preserved. Okay, so now let's suppose that my magnetic field is all in the sort of z direction, okay, zoop, 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 but it looks like this. It's going in, it's coming out, it's going in, it's coming out. So I have a field that goes like this, yeek, 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 so forth and so on. And it has a wave number k. So if I didn't do anything, if my velocity were 0, then this magnetic field would take eta times k0 squared to the k, which could be long, let's say. However, now I introduce my stagnation point flow. So what this thing is going to do is take all these field lines that are going this way, and squeeze them. So the characteristic distance between reversing field lines is going to get squished into this stagnation line. And it's going to get smaller and smaller and smaller. And so the distance over which diffusion has to act is getting smaller and smaller and smaller with time. And so diffusion will be enhanced. Okay? So for instance, let's see if I can find a solution of this form, where now my wave number is a function of time and my amplitude is a function of time. Okay? So I just say, let's suppose that the magnetic field looks like that. What the heck? And it varies only with y. And I have to have that initially, I haven't done anything yet, so k at time 0 is equal to k0, and b at time 0 is equal to b0. And you say, okay, can I find a solution for this thing? And okay, I substitute all those ansatz into the induction equation, okay, and then I have to have a derivative that comes from taking the derivative of B plus another time derivative, which is derivative of K. My wave number is changing and my amplitude is changing, okay? And then on this side, I have the diffusion bit, and this is the squishing bit. Okay, so I have these 4 bits. Okay, I would like this to apply for all values of y. Can I do that? Well, yes, I can do that, provided that, you know, this one and that one are the same, and this one and that one are the same. If I can arrange that, then I have found a solution that is y-independent. So all this thing can work, provided that the key by dt goes like alpha k, and the b by dt goes like that. So b is decreasing exponentially, and k is increasing exponentially. So my wave number is getting bigger and bigger and bigger exponentially fast. So the scales are shrinking exponentially fast. All right? And my amplitude is decreasing exponentially fast. All right? So if I put it all together, this is my wave number that is going up exponentially fast, and this is my solution. Okay? So I have a decay that is greatly accelerated with respect to the other one. Enormously faster. All right? Because, you know, it's like it's an exponentially decay with an exponentially increasing wave number. So I suddenly speeded this thing up by an exponential factor. And why is that? Well, it's because of this. It's because if I keep squishing stuff into an advection point flow, I can squish them. The distance between characteristic scales is decreasing exponentially fast. As we shall see later, this is a typical property of the geometry of axisymmetric stagnation point flows. So in the vicinity of the stagnation point flows, the existence of these 2 very strange trajectories, so these 2 invariant manifolds, which are the, you know, stagnation lines, makes it possible to have this exponential stretching along one direction and exponential contraction along the other direction. Okay? So there's something about stagnation points that makes these exponential processes come in. Now you're going to say, this is completely irrelevant because, you know, if I take a normal fluid, how many stagnation points am I going to find? None. I mean, maybe 1, you know, where I splatter this thing against the table, there's a stagnation point, but everywhere else, there are none. But actually, that is not the case. It's not the case for the following reason. If you take the typical, we can use the blackboard. We get to use the blackboard. This is so cool. Okay, so if you take the typical flow, right, you take a typical velocity that is moving stuff around and is doing its thing. I can take locally this flow and divide it into a bunch of things. One of them is a displacement. So there's going to be a straight displacement where it takes the axis and just move them along the flow. There's another thing which is, you know, basically a solid body rotation. Okay, so there is, this thing can be turned into a homogeneous displacement, a rotation, solid body. So this is encoded by an orthogonal matrix. And then there will be a deformation. And guess what? If you look at the deformation, it looks none other than some kind of stagnation point flow. So at any point, a flow will always look like this, this, and that. And I mean, I'm not going to prove it for you, but uniform displacement doesn't do anything to anybody. Uniform rotation confuses everybody, but doesn't do anything to them. But this thing here is exactly what we're talking about. And it will occur everywhere in a fluid, unless it's a very strange fluid. I mean, unless it's a really strange flow. So if you have a random flow, everywhere is like this. So everywhere you have a stagnation point flow. Okay? So long as the flow is complicated and is messing around with things, it will always do that to you. And in a little bit, when we discuss dynamos, we're going to get this thing in spades. So don't worry. But the bottom line is that I can greatly accelerate decay in the you know, near a stagnation point, and these stagnation points actually in a complicated flow exist everywhere. So, okay, sorry, I've done that. So let me show you what the consequence is of having this, because, you know, you have this paradoxical situation. Rm is enormous. Diffusion is irrelevant, except that it's not irrelevant, and except that it's relevant only in these tiny little areas, you know, where you build these enormous gradients. And, you know, these little areas in where you build enormous gradients and everything happens really, really fast in the neighborhood of these enormous gradients are in this tiny little region someplace. And so, you know, you think, well, you know, what am I thinking here? Well, what picture should I have in mind? Well, this example is a preamble to start thinking about the geometry of these flows. Consider a very simple case in 2 dimensions so that we don't get too confused. So in 2 dimensions, I can write the magnetic field as the curl. Well, okay, so it only has an x and y component. Nothing is coming out in the z direction. I can write the B in terms of a vector potential. The vector potential only has one component, which is, you know, in the direction coming out of the board. And so my magnetic field is encoded by d by dy of A minus d by dx of A. And A is normally called a scalar vector. It's a scalar potential, which is called a flux function. Okay? And I can guarantee that if you take 2 closed circuits of A, the difference in A value is the amount of flux, because of the theorem that we said before, that the amount of flux of a surface is the integral of A along the circulation. Okay. So in 2 dimensions, magnetic fields become like scalars. They're encoded by a single scalar, which is the flux contained within a closed loop of radius, whatever you want. Okay. Let's assume that I have a velocity, which is also 2-dimensional, and let me make it incompressible. So this velocity preserves volume. I'm not squishing anything, and I'm not expanding anything. I'm just shearing things. I'm just pulling them this way and squishing them this way, so that, you know, volume is not created out of nowhere. Okay. We had an uncurled version of the equation. If you put it in, if you substitute that thing over there into the induction equation, you find that the evolution equation for A, for the flux function, is just the scalar advection equation plus diffusion. So the vector potential is carried around by the fluid and is diffused. Okay? It obeys a scalar advection diffusion equation. All right. Let's think about this. Let's suppose that we have some kind of region enclosed by a curve on which V dot n is equal to 0. So there is a region with no outgoing flows. So all the flow is contained inside this region. There's no velocity radial that is going, you know, normal to this curve. So I'm considering a domain like a bucket. Think of a 2-dimensional bucket. Nothing is going out of the bucket, okay? Everything, I'm stirring the bucket any way I want, but there isn't stuff leaking out or into the bucket. And A is just the amount of flux that is contained into this bucket that has to be conserved because the bucket itself, by definition, is a flux surface. So whatever flux I have at the beginning, I have it. All right. Let's have a look at what's going on. Consider a region, da-da-da-da. Okay, let me introduce an average over that region. Okay? Then I can dot A into this thing here, muck it around, and I can guarantee that what you're going to get is that the time rate of change of A squared is given by minus 2 eta times the average of the gradient squares of A. Okay? So this term can move stuff around this bucket, but really, if it makes it big somewhere, it has to make it small somewhere else. So it doesn't contribute to the average. Now, normally, this thing here is called the variance. And this equation tells you that the variance of A, okay, the amount of fluctuation has to monotonically decrease because this is a positive quantity and there's a minus there. All right? In mathematics, this thing here is called a maximum principle, which means that since the variance of A has to start, if the beginning A is bounded between plus and minus 1, you can stir it any way you like, but you're never going to get anything bigger than plus 1 or smaller than minus 1. Why? Because you're just moving these things around. You're not adding them. Okay? That is why if I give you a cup with milk and coffee and you stir it, there's no way that you can stir it to get infinite milk and infinite coffee. All you get is cappuccino, caffè latte. It goes to the average value. Okay? You cannot stir it to say, can I squish all the milk in one corner? So it's like, you know, if I give you hot water and cold water and you mix them, there's no way to mix them to get very, very hot water and very, very cold water. It violates, you know, increase of entropy. The increase of entropy is a statement of the maximum principle. So this thing tells you that it can only decay towards the average. All right? So, for instance, suppose that you have a case where the average is 0. Average is 0 means there's no net flux over this bucket. For instance, it was half going on this side and half going down that side. So that the net flux was 0. And you start, so it's the same thing. Hot water, cold water. You start stirring it, what you get? You get, lukewarm water. You get cappuccino. So suppose that the average was equal to 0 initially, then it will remain 0 forever, okay, because that thing is a flux surface. And so A has to decay to 0. It's the only thing it can do. So if I have just as much flux going up as going down, and I start mixing them in 2 dimensions, I end up with no flux at all, identically 0 everywhere. This thing will demagnetize. The question is, how long does it take? Well, how long does it take? It depends whether you stir it or not. You know perfectly well that, if you take a glass and you put gin in it or vodka in it, and then very carefully you add your vermouth and you don't stir it, it's going to take 6 hours before this thing turns into a martini cocktail. Now, 6 hours is a very long period of time to wait. And so if you're James Bond and you have to go and save the world from the evil guys and drink your vodka martini, you ask for it shaken, not stirred, because otherwise it just takes too long. By the way, it's an interesting question what's the difference between stirring and shaking a cocktail that took me 5 years in Cambridge to figure it out. But I'll give you a hint. You can shake a vodka martini, but you must never shake a gin martini. And the reason is that if you shake a gin martini, you bruise the gin. What that statement means, if you're very nice to me, I may explain it to you tomorrow. It's a very, very strange thing, and it took me 5 years in Cambridge to figure it out. Bruising gin. What the hell does that mean? Anyway, so you must not, you can stir vodka, you can shake vodka, but not gin. Okay, so James Bond is in a hurry. He wants his martini right away, so he shakes it. So if you shake this thing, you get your martini right away. If you don't shake it, you have to wait very long time. That has to do with diffusion, many hours. So depending on what you do, you can accelerate it to the point that how long it takes doesn't even depend on the diffusion at all. It just depends on the shaking. Okay, so if you shake it enough, if your velocity is sufficiently complicated, you can have a situation in which the time it takes to homogenize everything, which in this example is get rid of all of the flux, becomes independent of diffusivity. And this is where the paradox comes in. And you say, well, even if the diffusivity is 0, identically 0, you say, hell no. If the diffusivity is identically 0, you're screwed. You cannot destroy the stuff. And so if it was 1 at the beginning and -1, it will remain between plus and -1. But so long as you have some, then you can destroy it. But it has to be non-zero. It can be as small as you like, but non-zero. Okay? This is what's so paradoxical about this thing. So the limit is very singular. You cannot have Rm infinity, but you can make it as big as you want. Then, if Rm is as big as you want, but non-zero, I claim that there's a way of stirring this fluid so that the time it takes for this thing to homogenize, to destroy all of the flux, is independent of eta. It's independent of the collisional diffusion. Well, okay, if it's independent of the collisional diffusion, what does it depend on? Well, it can only depend on V and L, where L is the characteristic scale of the velocity, and V is its characteristic size of the velocity, because VL is the only thing that I can get that has the right dimension of diffusion. So this is time, L squared over VL. This is an effective diffusivity that is associated with a flow with velocity L and characteristic scale little l. This big L here is the size of the container. Okay? So this, think of it as the size over which you stir. It's the coherence length of the velocity. Okay, so that's it. This is the time it takes, and it's independent of diffusivity. It doesn't make any difference if the diffusivity is small, big, or in between. It just will happen. Okay? What does this imply? And you know it. You know you can do it. I mean, you did it 10 minutes ago when you made yourself coffee and you stirred, milk in it. Okay. If we substitute it into that equation that we had before, okay, this says, let me equate times and everything. Okay. So the time it takes to homogenize the large scale is just the square of the large scale. So this is the one that it takes to destroy the variance, right? A variance equation. Okay, so this is the variance, and this is this inverse characteristic time that it's independent of eta. On the other side, I have this thing here, and if you remember, the quantity that I had was the square gradients of A. Where is that equation? Square gradients of A. Okay? So notice that there's something very strange. It's singular. If this goes to 0, and I want this to be independent of this, if this goes to 0, this has to go to infinity. I have to have infinite gradients. My gradients are diverging. Okay? So the conclusion is that it has satisfied this, where these are the typical gradients of A. And then if I plug them into my equation, I recover this thing. The delta has to be L to the Rm minus 1. But it has to be Rm to the minus 1 in such a way that when I average it, it remains there. In other words, it has to be Rm to the minus a half everywhere. Okay? So what does that mean? It means that when you stir the coffee and everything happens in order one time, and it didn't take 6 hours for these two things to mix, how did it do it? Well, in order for diffusion to do something, it has to construct these tiny little scales. If it builds these tiny little scales, it means that your gradients have increased enormously. But they can't just increase enormously at a point. Because if they only increase enormously at a point, when you take the average, it gets diluted by the fact that, this point has no area. So it doesn't count. It has to have finite area. It has to be everywhere. So it's not that you just need large gradients. You need large gradients all over the place. And in reality with coffee and thing is that when you stir, the interface between the coffee and the milk becomes corrugated and it begins to go all over the place. And so everywhere you will have coffee and milk sitting next to each other, which means you have a very, very large gradient of coffee concentration. So the essence of turbulent mixing and turbulent diffusion, so this would be the turbulent diffusion, it has dimension of area over time, is that you have to be able to construct large gradients absolutely everywhere. Okay? So that so everything is still getting weirder and weirder, because on the one hand you say, if the magnetic Reynolds number is enormous, diffusion is irrelevant. Then you say, yeah, but if diffusion is irrelevant, I can't get anything done. And you say, okay, if you want to get something done and diffusion is tiny, then you have to build very large gradients someplace. Then you're James Bond and you're in a hurry, and you say, no, I don't know. Not only I want diffusion to act, I want the diffusion to act very quickly. I want to get rid of all the fluctuation right away. I don't want to have to wait diffusion times. Then the answer is, okay, we can arrange it, but you have to have large gradients everywhere. Okay? So at every location in the fluid, you have to have a finite probability that you're in the neighborhood of a very large gradient. That's what it means. Not that there is one everywhere, but there's a very fat probability that there's one nearby. Okay, if that is the case, then this is what is typically done in astrophysics, that you replace an advective equation. So that an advective equation is essentially a hyperbolic system by a parabolic one. This is the diffusion equation. And instead of having the collisional one, you see, we got rid of the u dot grad, and we lumped it all into this nice little thing here called the turbulent diffusion. And the turbulent diffusion does not depend on the collisional diffusion. It doesn't depend on Rm. This is the basis for the statement that sometimes you hear in astrophysics that everybody says, in astrophysics, all Reynolds number are of order 1. Okay? So all things are so undiffusive that they're actually very diffusive. And it's because, yeah, they're very undiffusive, but they're also very turbulent. Okay? So there is this magic that has been done that we've taken. We started off with an equation which was the advection diffusion equation for A with very, very little diffusion. And we ended up with an equation for A bar, for the average of A, that it's all diffusive and no advection. Okay? And the reason is because I have assumed that underneath there is a flow that everywhere looks like a stagnation point, that it can generate very, very large scales exponentially fast. Okay? This is the essence of this going from there to there. And I will make that statement slightly more precise, what that entails in a little bit, in the context of dynamos. Ah, here comes the dynamos. Okay, might as well make it a little bit more. So, I hope you guys are not too confused. But there is this funny business that, you know, turbulent effective diffusivities and whatever can lead to this surprising behavior, like being able to diffuse everything very, very quickly, even in a system that has almost no diffusion at all. And the essence is the fact that the interaction of the diffusion with the motion can lead to this accelerated, you know, to these very short time scales and very concentrated scales, very tiny scales, very large wave numbers. But that was all for 2 dimensions. In 2 dimensions, the magnetic field is just a scalar, can be treated as a scalar. In 3 dimension, we know that it can't. Why do we know that? Because I've already told you that in 3 dimension in general, you can describe the magnetic field as the lines of intersection of families of constant scalars, but I need at least 2 of them. So in 3 dimension, the magnetic field is like 2 scalars, 2 of them. Because it's a vector field, so it has 3 components, but it's solenoidal. So I can always get rid of one of the components in terms of the other 2. So the magnetic field is a funny thing. It's more than a scalar, less than a general vector. It's a solenoidal vector field, and it looks like 2 scalars. Okay. All right. So in 2 dimension, if you give me a scalar and I start stirring, the only thing that it can do is mix it quicker. And we asked that question, can you stir it in such a way as to make it diffuse even slower than it would have done anyway? And the answer is no, you cannot. Okay, so V equal to 0 is a lower bound. If you don't do anything, it will diffuse under its own steam. Whatever you do to touch it will make it go faster. You cannot slow down the diffusion by mixing it around. As soon as you start moving it, it diffuses faster than if you're not moving it. Okay? So, what about in 3D? Does it always lead to accelerated decay? In other words, now I have a magnetic field, and I start moving it. Can I make it decay less fast than it would have done otherwise? And the answer is, hell yes! I mean, you can move it in such a way that you even undo diffusion completely. In 3 dimension, you can get infinite milk, and you can get infinite coffee, except that it's not coffee and milk, it's the gradients of coffee and the gradients of milk, which I don't know why you would want to taste anything like that. But in 3 dimension, there is these situations where by moving things in an appropriate way, you can actually not just lead to the accelerated decay of the magnetic field, but actually to its growth. So there's a way of moving things around so you end up with more magnetic field than you had when you started. Okay? And how does it work? Well, we had this induction equation that has 2 bits. One of them is this line stretching, and the other one is the diffusion. In 2 dimension, the diffusion always wins. You can't move this thing in such a way that the stretching wins. But in 3 dimensions, you can. And it's for a very sneaky geometrical reason that hopefully I'll try to explain later. And so this thing here makes the magnetic field gets weaker. This thing here makes it go stronger. Who wins? Well, okay, that question has a name. It's called dynamo theory, which is a very complicated mathematical mess. And mathematicians can have as much fun as they want with dynamo theory. But the bottom line, to give you the punchline, is that in general, okay, if the magnetic Reynolds number is large and you start moving the fluid, this guy will always win. Okay? In general, I mean, you can construct specific cases where that is not the case. But in general, any flow that is kind of messy, complicated, and not symmetric, high magnetic Reynolds number will lead to the amplification of magnetic field. Will be an anti-diffusion. Will just kind of make the magnetic field grow. But it's very, very difficult to make it precise. And why is that? Because if you look what happens in a complicated flow, well, we've already seen that the gradients in a complicated flow grow exponentially fast. They get exponentially big. These wave numbers, you know, diverge and become exponentially large. So gradients get very, very big very quickly. What about stretching? Well, stretching is also exponential. All right? So you have two competing processes that both proceed at an exponential rate. So which one wins depends on who's got a bigger exponent. That is not something that you can answer by dimensional analysis, because dimensional analysis doesn't pick up exponential. Exponential have no dimensions to go with them. And therefore, you'll never answer a dynamo question by looking at dimensional analysis, which is what people were trying to do a long time ago when dynamo theory was in its infancy. And so, in a sense, dynamo action cannot be settled easily. You have to go into each case and figure it out. All right? So to give you an idea of the complexity of this problem, the first person ever to think about dynamo and dynamo action in this thing was in 1919. So we're getting around to about 100 years ago. Okay, Sir Joseph Larmor. So what was Larmor up to? Well, they'd invented the magnetometer. They pointed it at the sun. In fact, specifically, they pointed this thing at a sunspot. Because, you know, people had known about sunspots for a long time. There are these little dark splodges on the sun. So they pointed the magnetometer at the sun, and lo and behold, just after the turn of the other century, they figured out that sunspots were strongly magnetized. And this freaked out everybody. Why is that? Well, okay, people had known that the Earth had been magnetized for a long year. A long time since antiquity, everybody knew that there was a magnetic field of the Earth. People used it to, you know, to make compasses and stuff like that. So there was no surprise that the Earth was magnetized. But why was that? Because the people that found it unsurprising were somewhat ignorant. They hadn't realized that the center of the Earth was way, way above the Curie temperature for permanent magnetization. They simply didn't know that. And so to them, the Earth was just one big permanent magnet. That's it. End of problem. But, you know, the center of the sun, of the Earth, not only is above the Curie temperature, so you can't have a permanent magnet. Worse than that is a liquid core. So, you know, but they didn't know that at the time, you know. At the turn of the other century, they didn't know that. But so they thought, okay, it's perfectly normal for a planet like the Earth to be magnetized, but the sun is one big sphere of gas. Why on earth should this boiling mass of gas be magnetized? This is totally bizarre. You know, it can't be a permanent magnet. I mean, there's nothing permanent about it. This thing is boiling. So why is it magnetized? So in this famous paper in 1919, Sir Joseph Larmor looked at 3 possible mechanisms that would lead to the magnetization of a sunspot. And to be perfectly honest, I can't even remember what the other 2 are, and nor, I think, does anyone else. But one of them, he said, well, you know, suppose that you have a current that is just flowing into this electrically conducting fluid. No, you know, if you have a flowing current, it's going to generate a magnetic field. Ta-da! Then, of course, this fluid is moving, so this magnetic field is going to be moved around. And so it's going to generate an inductive current. What about if the inductive current is the very same current that you had in the first place to generate that magnetic field? Then this thing will self-sustain, and this fluid, so long as you keep moving it in the right way, will remain self-magnetized. So that was the essence of a dynamo 100 years ago. And okay, that was a brilliant idea, so everybody set about trying to write down a flow. You say, okay, what does this flow look like that has this funny property that the currents are consistent with the magnetic field, blah, blah, blah. All of these things. And what followed was 20 years of various people, but mostly Cowling, writing down theorems that said all of the things that couldn't work. In fact, they're all called anti-dynamo theorems. So he said, axisymmetric flows. No, that's not going to work. Theorem number 1, no axisymmetric dynamo. Okay, how about 2-dimensional flows? Hell no, we already know that. They only lead to... How about flows that are purely colloidal? No, that's not going to work anyway. So he just, you know, spent the next 20 years proving all the things that just wouldn't work. Okay? Then, you know, the war broke out, which kind of, you know, puts a spanner into anybody's enjoyment of life. But nevertheless, it's amazing that even during World War II, Biermann and Cowling, I mean, one was German, the other was English. They kept, you know, merrily and happily working and conversing with each other about these matters, which I find, you know, remarkable. But anyway, so they did. And after the war, there began to emerge these first dynamo models. But if you saw what they looked like, they were so artificial that you say, God, you're never going to explain why a sunspot is magnetized on the ground of one of these things. So one of the earliest rigorous demonstration of dynamo action was this thing called the Herzenberg dynamo that consisted of 3 rotating spheres. Okay, so you have a sphere, a sphere, so your fluid consists of a sphere, a sphere, a sphere, and they're all at a funny angle, and you have to rotate them in such a way that the dipole induced by this one goes into this one, which induces this one and induces this one. And if you try to do it with 2 spheres, it won't work, but it will with 3. Okay, so they were very artificial looking. And so the question was, if you want to magnetize a sunspot or the sun, what do you do? And so in the middle 50s, Eugene Parker had the right idea. I mean, he just got it dead on. And his idea was what every good, I suppose I should say, statistical mechanician would do, which goes back to what I was saying earlier. If I give you an equation and you can't solve it, you can do one or 2 things. You can linearize it. Well, the induction equation is already linear. You can't linearize a linear equation. So that won't help. The next thing is try if you can solve the average of that equation. So what Gene Parker figured out is like, what I'm after is not, the magnetic field is going to be this horribly fluctuating quantity. We know this because diffusion is going to generate all these little scales and everything. But I don't care about the little scale. What I care about is the mean. It's the average magnetic field. What I want to know is, why does the sun have a dipole field? I don't care about all the little details. All right? So he said, let me average the equation. And lo and behold, from a mathematical standpoint, whenever you average an equation, it does 2 good things. First of all, if you have a rapidly fluctuating coefficient, it gets rid of it in favor of a slowly fluctuating coefficient, and therefore your solution is so much more differentiable than the original one. And second, in the specific case of dynamos, once you looked at the averaged equation, it did not have any of the unpleasant anti-dynamo theories that the original equation had. So the average dynamo equations don't have the anti-dynamo theory. So you can look for axisymmetric solutions. You can look for, anything you want. And suddenly your mathematical problem becomes a lot easier. So this solution to the problem in the 50s was so brilliant that it was universally ignored by everybody. So the world yawned, and nobody read Parker's paper except possibly, Mrs. Parker and then Gene Parker's mommy or someone. And that was the end of that for 10 years. And then 10 years later, in the middle 60s, 2 completely different groups of people, this guy called Stanislav Braginsky in the Soviet Union, developed another rigorous treatment also based on averaging. So what he said is like, okay, a purely axisymmetric flow will not be a dynamo. What about a flow that it's almost completely axisymmetric, but it's got this tiny, tiny little deviation from axisymmetry, but they're really tiny? Will that work? And then he was able to derive, what this average over little fluctuation would do to the mean. So he got a dynamo to work. And then these 3 Germans, Steenbeck, Krauser, and Radler in Potsdam, in the 60s also, essentially got another averaging procedures based on the use of Green's functions. Those of you who know what Green's functions are, good for you. Those who don't worry. It's a way of doing averages. So they also wrote down an average equation. And all 3 methods, or Parker's method of averaging, there was very much empirical. So he was thinking, think of these events. I'll go into what these events look like in a second. But all 3 methods gave an answer that worked, and they look completely different. And it took the better part of the next 10 years to figure out that these 3 completely different approaches that don't look anything like each other are in fact the same thing. And the same thing is now known universally as mean field electrodynamics. And I'm going to give you the version of mean field electrodynamics, which is mostly due to Roberts, and Paul Roberts, that is. This field is full of Roberts. So whenever you bump into a Robert, make sure that you know the first name, because otherwise you're dealing with the wrong Roberts. So this is Paul Roberts, the guy that used to be in Newcastle and now is in UCLA. And it's also the one that is, for instance, in Moffat's book. All right? But so that brought us, let's say, in the sort of middle 70s or the 70s. And at that point, everybody was happy because you had this beautiful theory called mean field theory that just gave an answer and everything worked and everything was fine. And so some people felt, we should think of something to screw this up because, everybody's happy. We seem to have solved the problem. You can't just leave it to this. So what can we do to screw it up? And so what they could do to screw it up was that these two guys, Weinstein and Zeldovich, started saying, yeah, but this mean field thing isn't going to work so well when the magnetic Reynolds number is very large. It makes all sorts of assumptions that don't work. And so they introduced this thing that in astrophysical situation, dynamos had to work a large magnetic Reynolds number. Okay? They had to be, they called it fast. They introduced this idea of a fast dynamo, a dynamo that works even in the limit of infinite magnetic Reynolds number. And so then people went back and looked at all the examples of dynamos that were known, and they discovered they were all slow. So none of them were astrophysically significant. So people said, okay, well, let's produce an example of a fast dynamo. Let's just write down a flow that has the fast dynamo procedure property and be done. Okay, to make a long story short, there are no rigorous examples of flows that have the fast dynamo property, even though everybody is convinced that anything is a fast dynamo, but nobody can prove it. All right? Mathematically, with all the bells and whistles, you can kind of sort of prove it, but not really. And so the only rigorously proof that a velocity is a fast dynamo is one by Arnold, Zeldovich, Sokolov, and someone else that I can't remember who the fourth one is. And it's for a flow that cannot be embedded in three-dimensional Euclidean space. You need a really crazy manifold for this flow to exist. But if you try to, make it in 3D, you can't. So that's the only one for which there is a rigorous thing. So the reason why I told you all of this is that the induction equation is a linear equation. You think, how hard can it be to show that, these exponentially growing solutions exist and for these particular flows? Well, I don't know. It seems to be harder than you think. Okay, that's all I can tell you. 100 years have gone by. Lots of people are still working on dynamos. Some of us spent a lifetime working at these things, and we still haven't quite figured out what's going on. Some people went out of the way to screw it all up by pointing out that these dynamos don't work. I have to admit that I was one of those guys for which, I apologize profusely for everybody. But there it is. So the dynamo theory, there's something hard about it. And maybe because it's this business that it's a topological problem. Maybe I don't know what it is, but it's not easy. Okay? And so now I'm going to spend the next half hour plus some more time, tomorrow, trying to take you over this business of dynamo theory and why I think it's complicated. And then we should look at another thing that is also kind of sort of complicated, which is MHD turbulence. All right. So what's the deal with dynamo theory? Okay, so first of all, what is a dynamo? Okay, a hydromagnetic dynamo is a mechanism to generate magnetic fields throughout the bulk of an electrically conducting fluid. But the secret is that you have to do it in a compact space. Am I done? Oh, right. Yeah, no, that's perfect. Then let me just finish this and then I'll stop. Yeah. So then next, no, that's going to work out great. So let me just, so you can ponder about this thing. The secret is this, is that you don't want to do it in an unbounded domain. Why? Because otherwise you could do a dynamo this way. Suppose that I take one end of an of a magnetic field lines. You take another, end of a flux tube. Then I run that way, you run that way to the other corners of the universe. And of course the magnetic field in this tube has to go through the roof because we're stretching it. But that's not a dynamo because it's not in a bounded domain. That's just like I'm, stretching forever. So the secret of the dynamo is that you have to stretch these field lines, but always repack them into the same volume. So all the stretching has to occur in a finite volume. So think of it this way. You have a line in a finite volume. So you start with a line. This line almost moves with the fluid because, Rm is very large. So you start stirring this thing, and this line gets longer and longer and longer and longer and longer. So eventually, it's going to get as long as you want. So you think, oh, great, I've done it. I've created a dynamo because this line has become infinitely long. The trouble is that the gradients have also become infinitely long because this line will go next to each other an infinite number of times. And so the problem is, how do you assure that somehow, you're stretching it more than you're canceling it? And that is the essence of the dynamo problem. It's just overcoming this fundamental issue. How do you get line lengths to go faster than gradients? Okay? So tomorrow we'll do all of that stuff and a lot more beside. So stay tuned for the next installment. Okay, thank you.